Hello, students. Yeah. So you can see here the topic that we are going to discuss today is optics. Actually, optics, what is optics? Optics is a branch of physics which deals with light, how it is originated, how it propagates, what are its effects, the phenomena they exhibit. All this comes under one branch of physics, which we call it as optics. Now, what exactly we are going to study in optics here? Are we going to talk about the origin of light? Are we going to talk about propagation of light, or are we going to talk about the phenomena? So, actually, in your previous class, in your ninth standard, you have actually learned a part of optics, that is reflection. You have learned a part of refraction also, you have learned. So in this today's class, our main concentration will be on refraction through curved surface. That's refraction through lenses. That's our main focus here. But whatever, since reflection, those concepts were done in the last year, the refraction part of it was done last year. So I thought I will just revise it a little bit, and then I will slowly start with refraction through lens. Okay, so let's begin with it. So what is optics? Already I told you, it's a branch of physics which deals with light, totally about light. But if you see optics again, optics is divided into two more categories, subcategories. What are those? You have ray optics and you have wave optics. So what are these? Ray optics and wave optics. Ray optics is that branch of optics in which we will be treating light as a ray. A ray means, what is ray? A straight line indicating the light, and with an arrow indicating the direction of propagation of the light. So here we are actually considering light to travel in straight line. It's true to a certain extent. It's true. Light travels in a straight line. So keeping that idea in mind, we construct ray diagrams, geometrical figures in which we use straight lines with arrows. So something like this, straight line with arrow. The line indicates the light itself and arrow indicates in which direction it moves. So that is ray optics. What is wave optics? Wave optics, in that we are going to treat light as a wave. We take a concept of wavefront and we discuss certain phenomena of light based on the wavefront concept. So here we are purely concentrating on ray diagrams, geometrical figures we are going to draw to understand certain phenomena exhibited by light. So the first one in that is reflection. So let's begin with reflection quickly. We'll have a glance at what is reflection and the laws of reflection. We'll just talk about this. Actually, there are a few more things in reflection, like reflection through curved surface, reflection through concave, convex, curved surfaces, mirrors. But we are not going to talk about all that here because it's already done. I already mentioned to you. Yeah. So we'll just have a glance at what is reflection and the laws of reflection. So let's begin with it. So reflection. So reflection is one of the phenomena exhibited by light, where light hits a surface and it comes back to the same medium. After hitting the surface, it returns back to the same medium. So that phenomenon, we call it as reflection. Like when you hit a ball, you throw a ball to a wall, and then that ball comes back. So the same way, light also does the same thing. So that's called reflection. But reflection does not happen on all the surfaces. We need, whenever we deal with light, we need to talk about optical medium, because optical medium is the medium in which light can actually travel or show its certain behaviors and all that. So what is this optical medium? Optical medium is, most of the time, it's a transparent medium like glass, water, air, some oil. So these are the medium through which light can travel. So such medium we call them as optical medium. So even if reflection has to happen, a kind of optical surface has to be there. Means something like a transparent surface. But exactly transparent, if the surface is fully transparent, then we know that light can pass through that. So what can be done is, say for example, you have a glass surface like this. You do one thing, you make one side of the glass opaque so that the light can't pass through it. Usually we call it as silvering one side. And the other side is a glass. It's not necessarily glass always. Highly polished surface can act like a reflecting surface. Even if you see cars, metal body, vehicles, metal body, if you go and stand in front of it, you can see yourself there because it's well polished. May not be as good as how you see in your mirrors, but still there is reflection. So highly polished surface can do this work. Okay. Even spoons, if you keep a spoon or a steel plate and see yourself, you can see yourself. So well polished surface can behave like a reflector of light. But to get a better view, if you have a glass surface with one side opaque, I mean one side silvered, it will be the best thing. Okay, so say this now becomes a mirror. We call usually a reflecting surface as a mirror. So now let us say one ray of light comes like this, falls on this mirror. This ray, we call it as incident ray. We call this one as incident ray. What happens to this ray? I already told you, the ray will come back to the same medium. So like this. Does it come back along the same path? No, you can see it doesn't come back along the same path. But is it possible in any case? Yes, it's possible. If you hit it perpendicular to the surface, it will come back perpendicular along the same path, retraces the path. But always that doesn't happen. So this way, let us assume now. So this is a reflected ray. This is a reflected ray. Okay, now let me draw one normal. What is normal? Normal is a perpendicular line. Normal is a perpendicular line. Perpendicular to what? Perpendicular to the surface of reflection or reflecting surface. So here the mirror is a reflecting surface. So you can see white line and yellow lines are perpendicular to each other. That's a normal. So now the angle between this incident ray and the normal, we call it as angle of incidence, represented by I. And this angle between the reflected ray and the normal, we call it as angle of reflection, represented by R. So this is how the diagram looks like for reflection. Okay, moving ahead, with laws of reflection. There are two laws. The first one says that the incident ray, the reflected ray, and the normal at the point of incidence all lie on the same plane. You can see that here, very obvious. You can see incident ray is here, reflected ray is over here, and the normal is over here. And I've drawn it all on one page on a surface. So that becomes a plane. The rays, all the rays, actually normal is not a ray, but still, incident ray, reflected ray, and the normal, they lie on the same plane. Okay, then what does out of plane mean? It's like this, somewhat like this. Say there is a light. Say we have a mirror kept horizontal like this, and a ray of light comes, falls on the surface. This is the normal. Now, according to the law, the reflected ray also should be on the same surface, which is true actually. So you will never find a ray which is coming out like this. This way it doesn't come out. Ray falling on the mirror, which is on the plane like this. This is a plane. On this plane it is. The ray will not fall like this and does not come out of the surface like this. So if that happens, then the first law is violated. That doesn't happen. So the first law is given. The incident ray, the reflected ray, and the normal all lie on the same plane. The second one is very simple one, and most of the students love this law. The simple law which says that angle of incidence is equal to angle of reflection. I is equal to R. Okay. So if you have a reflecting surface, say, so this is a mirror. There's an incident ray coming like this, falling on the surface, and let us say it makes an angle of 60 degree. Then I ask you, what will be the angle of reflection? So you should now tell me immediately that this angle also is equal to 60 degree, whatever be the condition. Okay, angle of incidence is always equal to angle of reflection. So that's about reflection. Yes, now coming to refraction. So refraction of light. So what is this refraction of light? I told you in the beginning that light travels along a straight line. So does that mean that always if it starts like this, it will go continuously like this, no matter whatever happens in between? Medium changes or anything happens, it never gets deviated. Does it go like this only always? The answer is no. What happens is when the medium changes, the light has a tendency to bend. Obviously, it will maintain that straight path. I mean, straight, it doesn't go curve. When I say straight path, I mean to say it doesn't go like this. It goes straight. But the thing is, it bends like this, but still follows that straight body. Okay. Yes. So refraction is that phenomenon in which the light rays bend when the medium changes. Okay. When it enters a different medium, the ray bends. So that is refraction. So let's write it. It's a phenomenon in which light rays bend when the medium changes. Okay, so let's understand with the picture. Let me take one medium, say a glass medium, or let us say water in a water medium. Some tank is there, let us say water is there in the tank. like this. Okay. So this is water medium. And outside, what is there then? Let me take outside air. When I say air, I also mean that it is vacuum, or I can even sometimes call it as free space. So when I use the word free space, it means vacuum, or I can also use the word air, because air and vacuum, they are not exactly same. Vacuum means there are no air particles, no molecules, nothing. But in air, there are certain gas molecules and all. But whatever it is, they are very close. Their nature is very close to each other. So almost we consider air and vacuum to be the same almost. Okay, approximately. So when I say vacuum or air, I mean to say the meaning is the same. Okay. Now, water is there and outside there is air medium. Now, light is coming in the air medium. It's in the air medium and it's coming like this. And now it touches the interface of the two media. What is that interface of the two media? This is the interface of two media. Means it's a boundary which separates the two medium. Above that you go, it's air medium. Below that you go, it is glass medium or water medium, whatever it is. So that is interface. Okay. So the ray of light coming from air falls on this interface. Now it's about to enter water medium. Something is different here now. What happens if you see the medium only, you'll feel air, it was really easy to move, right? Because obstructions were very little in air. Gas molecules were quite far apart from each other, so light easily could move. But when you think about water medium, water molecules very closely, not as close as glass, but whatever it is, compared to air molecules, they are closely packed, water molecules. So light will find a little difficult to move in that. So obviously it will slow down. So its speed changes. So because the speed changes, the bending happens. So it's something like you see, say you're going in a bike and you're on a highway, you go very fast, maybe at 100 kilometers per hour speed, maybe, or even more. You're going very fast because there are no other vehicles. It's very clean road, no much traffic. But then you enter a city where there is traffic, a lot of traffic. And the traffic is moving very, very slowly, heavy traffic. So what you can do, you have to go slowly. So your speed slows down. So same thing happens here with light. But light has one tendency, that is, no matter whatever be the condition, no matter whatever be the situation, it wants to reach its destination in that particular time which it was supposed to reach. Actually, here the light was supposed to go like this. The light is supposed to go like this. So then it comes out of water. So there was some time for it to reach from here to here, right? Some time it would have taken if it would have gone without that water medium. So in that time only, it has to do that job. That is a tendency of light. So what it will do now? It is slowed because the jam is more here, the traffic jam, like traffic, heavy traffic, like that water molecules are very close, and so its speed has come down. But whatever it is, it has to reach the other end in the given time, no matter what is the situation. So obviously it will search for shortcut. It will try to go in a path which is easier for it. Slow, but still it can reach on time because the path is smaller. That's what you will also try to choose, right? So suppose you are stuck in a heavy traffic. What you will think of, you will think whether there is any shortcut or any side where I can move on little easily. So you will try for some shortcut and you will just try to escape from there, right? So same thing the light will do. And the light's tendency is it's punctual. Punctual, it doesn't want to be late nor early. That's the tendency of light. So light will choose a shortcut now. Yes. So it will choose a shortcut. So shortcut means shorter path. So it will choose a path somewhat like this, shorter distance. Correct now? Yes. So this is why the light bends. That's the reason why light bends. So now let me draw a normal to this surface. So this is a normal at the point of incidence. Okay, fine. So this is the original direction. This is the incident ray. This is the incident ray. This is the refracted ray. And this is the normal. Okay, fine. Now, angle between the incident ray and the normal, we call it as what? Angle of incidence. Angle between the refracted ray and the normal, what do we call it as? Angle of refraction. Yes, correct. Now, what is this angle then? What is this angle? The ray was supposed to go like this, in this direction, but it took a new path like this. So how much it got deviated? So much it got deviated. So that angle, we call it as angle of deviation, written by letter D. So D stands for angle of deviation. Angle of deviation. Fine. You can give a formula now for angle of deviation. If you see this diagram properly, you can see that this angle is I. And exactly opposite to that, this is angle. We call it as vertically opposite angle. You remember in mathematics, vertically opposite angle, they're always equal. So this also is I. Now I want to know what is the formula for this angle. So if you take I, from that you remove R. I minus R you do, you will get D. So I minus R. So this is a formula for deviation. Fine. So if you observe here the light came from air medium and entered water medium. Will the situation be the same if the ray goes from water to denser, water to air? No, the situation will be slightly different. So here, medium plays a very important role, and the nature of the medium also. So air looks like little rarer medium. Rarer means little lighter medium. What is that rarer? You will understand it very soon. Okay. Water is little denser medium. Denser means little heavier. Heavier. Here I don't mean denser means more density. I'm not talking about mass by volume density. Density is mass by volume, right? I'm not talking about that density. Here when I say rarer or denser, the medium is little lighter and heavier. That doesn't really mean that it should be more massive per unit volume. No, it's not the mass by volume concept. It's called something called optical density. It's called optical density of the medium. Now, optical density is not mass by volume. It's not mass by volume. Please understand this. Optical density is not mass by volume. Then what is optical density? Optical density means if the medium is more dense for light, means it's making light to move more, making light's movement more difficult. Such medium we call it as optical denser. Okay. Rarer means light will feel a little easier to move there. Then it is optical rarer. But you're going to talk about this, we are going to understand about this more in the next part of it. So we will do that discussion a little later. Before that, we'll just see the figure. Like if the light was going from water medium to air medium, then how it will look like. Let's just have a understanding of it. So let's take water medium. Okay. So this is water medium. This is air medium. And now the light is coming from water and entering air medium. Light is coming from water and entering air medium like this. So this is the incident ray. I'll draw a normal. This is a normal. So this will be the angle of incidence. Okay. The ray has to now bend. Obviously, we know that now because the medium has to change. So how it will bend now? Previously, we saw that the ray bends towards the normal. It was bending towards the normal. So when the ray goes from rarer to denser, the ray bends towards normal. But now it's going from denser to rarer. Obviously, you know now it should bend away from the normal. But exactly what is happening there? Again, the same thing. In water, it was having a difficulty in moving, so its speed was less. Now it enters air where it's finding it easier to move, so it will go faster. So what will happen? I told you, light wants to reach at a given time, not early, not late. So now since it's going fast, it's expected to reach its destination earlier, which it doesn't want. So what it will do? It will take a long route and waste its time and see that it reaches at the given time, not early. So for that, only option is it can take a long route. That means it should go like this. It was supposed to go like this, but it changes the route like this. So if it had gone like this, dotted lines along that line, then it would reach early because it's already faster, right? So what it will do, it will change the route, it will bend further, take more time to reach that particular border. Border, if I say this is a border, to reach that, it will take more time. Okay. I mean, not more time, I mean, given time only. Otherwise, it would have reached earlier. Yes. So this is what exactly happens in the case of denser to rarer. So from denser to rarer, it will bend away from normal, away from the normal. Okay. So what is this angle? Angle between the normal and the refracted ray is angle of refraction. Okay. As you all know now, this is angle of deviation. Original path and the deviated path. So that is angle of deviation. Now what is this deviation equal to? Let's figure out that. You can see here this is angle of incidence, exactly vertically opposite. If you see this one, this angle is exactly vertically opposite. So this angle should be equal to I. So this angle is R. If I subtract I from that, I'll get D. So it is R minus I. So D is equal to R minus I. Previously, we had got I minus R. So if it's from rarer to denser, deviation is I minus R. If it's from denser to rarer, it is R minus I. Got it? Yeah. Now we will talk about laws of refraction. I don't have to explain the first law. Here also there are two laws. First law I don't have to explain much because it is just like the first law in reflection. Only thing is you will have to use the word refraction here. That's it. So here also you can see the incident ray, the refracted ray, and the normal. They all are lying on the same plane. I have used one paper, and on that paper all the lines are there. If they were not lying on the same plane, then I had to use one more, like something to show that the line is coming out or something. I couldn't draw it properly on the paper, right? Yes. So since I've drawn all the three lines on the same paper, that means they are on plane. Okay, let's write that. So the incident ray, the refracted ray, you have to be careful with this word, refracted ray, and the normal. Normal is not a ray. Some students write normal ray also. It's not a ray. And the normal at the point of incidence, all lie on the same plane. All lie on the same plane. Yeah. The second law is very, very important one, and that's called Snell's law. Snell is the name of a person who gave this law, who formulated it. So Snell's law. What does the Snell's law say? I'll write the mathematical form first, and later on, slowly, we will see the statement. Mathematically, Snell's law is given like this. Sin I divided by sin R is equal to a constant. So what does I stand for here? Angle of incidence. R stands for angle of refraction. Is a constant. Okay, what is that constant? We'll check out that later. Yeah. So I'll just tell you what this means now. The mathematical form, what does that mean? So for that, let me assume a refracting surface. This is the interface which separates the two medium, and the two medium which I'm taking in all the three cases are the same. Air, let me take water here. The same air, same water. Here also same air, same water. I'm not changing any medium here. What I'm going to do in the three cases is I'm going to send the light at different angles. So let me see what happens. In the first case, let us say light is incident this way, and obviously the rays going from rarer to denser, so it will bend towards the normal like this. So in the first case, it's like this. Second case, I'll just increase the angle of incidence a little bit. I'll bend the ray a little more. So you will find that actually the angle of refraction also is going to change. How it's going to change, you will understand. That's what the formula is for actually. So as in the third case, I'll bend the ray further. So again, the angle of refraction also is going to change further. So in all the three cases, angle of incidence is different. So angle of refraction also is going to be different. For different angle of incidence, there is different angle of refraction. I'll call this angle of incidence as I1 first case and R1 first case, I2 in the second case, R2 in the second case, I3 in the third case, R3 in the third case. Okay. So according to the Snell's law, if I apply that law to the first case, I get to see sin I1 by sin R1 is a constant. What constant? I do not know that. In the second case also, if I try to find sin I2 divided by sin R2, I get a constant. What constant? I do not know that. Sin I3 divided by sin R3 again is a constant. What constant? I do not know that. Okay, let me say roughly I find this value, and let me say that value is equal to 2. Surprisingly, the ratio when you take in the second case also, you will get 2 only then. In the third case also, you'll get 2 only then. So what is special in this then? Okay. So what is this 2 indicating? I told you keep the medium same, air, water, air, water, air, water, all the cases. And what I did was I changed the different angles. I changed the angles of angle of incidence in the 3 cases. And I found the angle of refraction, and I took the ratio like this. I found that the number for this pair of medium and for that same light, for different angle of incidence, different angle of refraction will be there. And when you take the ratio, it's a constant. You're finding it here. Actually, that constant will change if you change one of the medium or both the medium. So instead of what if you take glass, you're going to see that this value will not be 2 then. It will change. Same way, if you change both the medium also, obviously it's going to change. So that means I can see that this value this thing, so I'm seeing that this value actually depends on something like medium. Yes, yes, exactly. Because if I change the medium, I told you this is going to change. So I feel that this should have something to do with the nature of the medium. And that is correct. We will see that slowly, what that constant is, what it indicates. But observe one thing. Since this comes to be a constant, you can clearly see that for different angle of incidence, there will be different angle of refraction. So these two will keep changing if angle of incidence changes, angle of refraction changes. But totally, the ratio should be a constant. And for given pair of media, that's a constant. And for given light. That means that constant purely depends on the medium. So what does that constant tell us now? As I told you, constant talks about the nature of the medium. So what is that constant called? That constant is called as refractive index of the medium. Refractive index of the medium. So the constant which we are interested in now, this constant, that is called refractive index. When I say refractive index, I have two ways of expressing refractive index. One is absolute refractive index, one is relative refractive index. Now, as I told you, talks about nature of the medium, refractive index. Both the refractive index talks about nature of medium. But the problem is, anything in this world you see, everything is comparison. Not only your marks. Your parents compare your marks with your siblings or with your neighbors, your friends. It's not only that, everything in nature is actually comparison. If I say this pen is a long, is it necessary it should be long? If I keep this close to it, then yes, this is long. But if I have a pen which is longer than this, then no more this will be longer. Like if I say there is a line and this line is the shortest line, I say, then I will draw one more line, or somebody will draw one more line and say, see, there is one more shorter line here. So everything what we speak here, everything is relative. It's relative with something with respect to something else only we are speaking. So when we talk about the nature of the medium also, we have to talk about the nature of the medium with in comparison with some other medium. So you can't just say this medium is like this, not good, not or very good. No, in comparison with something, you should say it's good or not good, right? Yes. So when we talk about nature of medium, comparison comes. But I have used the word relative refractive index. So there clearly you can see that it is comparison. But I have used one more thing, absolute refractive index. Now, absolute word sounds that it should be the real value. But though it is real value, it is still a comparison. Then what is the real value? What is absolute then? Absolute also means comparison, yes. But in that case, you're comparing nature of one medium with something which is a standard one. So here if you see, standard means air seems to be a little standard or vacuum seems to be a little standard. Because like what happens to speed of light in vacuum? Everybody knows speed of light in vacuum is 3 into 10 to the power 8 meter per second. And it's a known value and it's not going to change in vacuum at all. It's going to be the same. So that will be taken as standard value here. So absolute value of any medium, refractive index of any medium will be in comparison with vacuum. And that is absolute value. So let's talk about it. Absolute refractive index. Absolute refractive index. Absolute refractive index. Okay. So in general, refractive index is represented by the symbol n, small letter n. Some books also use a symbol mu. Okay, I'll be using this symbol n for refractive index. Absolute refractive index also is the same symbol n. So what is this absolute refractive index? Actually, refractive index itself talks about the nature of the medium, I said, right? So it actually tells us like in that medium whether light can go faster or slow. So finally, it is something related to the speed of light in that medium. So absolute refractive index is something that tells you like in that medium how slow light can go or how fast a light can go. So the formula for the absolute refractive index is C by V. It's a ratio of speed of light. C stands for speed of light in vacuum to the speed of light in a medium. In the medium. So C stands for speed of light in vacuum, which all of us know the value. V stands for speed of light in in that particular medium, whose refractive index we have called it as N, absolute refractive index. Okay, so we are comparing the speed of light with that in vacuum, in the medium with that in vacuum. So that becomes absolute refractive index. So let's understand the deeper meaning of this. So this is just a formula. Refractive index is speed of light in vacuum to the speed of light in medium, that ratio. Fine, let's understand the meaning. Uh, Let me say that the speed of light in glass is 2 into 10 to the power 8 meter per second. So speed of light in glass is 2 into 10 to the power 8 meter per second. Can you calculate the refractive index of that glass for me? Absolute refractive index. Can you find it and tell me? So absolute refractive index of what I'm asking, glass, no? So symbolically I'll write it like this. So this is the symbol for refractive index or absolute refractive index or general refractive index. But this is refractive index of glass now, I'm talking in particular. So I'm writing here Ng. But absolute refractive index, no? Absolute refractive index is always in comparison with air or vacuum. So usually we write it as Nga. What do I mean by Nga? Nga means refractive index. Ri stands for refractive index. Refractive index of glass with respect to air. In comparison with air we are doing. So that is absolute refractive index. Refractive index of glass with respect to air. If you don't write A also, that's fine. Because some books they just give Ng. So where A goes? So it is in comparison with what, you may be wondering. So you don't have to think much about it. If nothing is mentioned, it is always the absolute value is in comparison with air or vacuum only. Okay. So now I'm asking you to calculate the value for refractive index of glass. I gave the speed of light in glass for you. You know speed of light in vacuum is 3 into 10 to the power 8 meter per second divided by speed of light in the glass is 2 into 10 to the power 8 meter per second. You can see this cancels, unit cancels. So please make a note that refractive index has no unit. No unit. Both are speed ratios, so the unit will cancel and it will not have any unit. So you ended up with refractive index of glass. Absolute refractive index of glass is 3 by 2. You can even write it as 1.5. Okay, so what is the real meaning? I got refractive index of glass as 1.5. So what does the value tell you? The value tells you this. See, very interesting. The value tells you this. You know, Ng, refractive index of glass is speed of light in vacuum to the speed of light in glass. And you got that value to be 1.5. So if I write it like this, speed of light in glass is C divided by 1.5. C divided by 1.5. So what does this tell you? It tells us that speed of light in glass is 1 by 1.5 times the speed of light in vacuum. That means in that medium, in which medium? Glass medium, the speed of light has reduced by 1.5 times. Times what? Speed of light in vacuum. So speed of light in vacuum is a standard. So in comparison with that 3 to 10 to the power 8, in glass, if you see, its speed has come down by 1.5 times. So that's the meaning of refractive index of a medium, absolute refractive index. Suppose I say refractive index of water. When I write like this, I'm talking about absolute refractive index in comparison with air. I say the value is 4 by 3. The value is actually 4 by 3, which you can write it as 1.33 also. So what does this tell us? That means if light enters water, its speed is going to slow down by 1.3 times. So the meaning of refractive index is, so speed of light reduces by 1.33 times in water. That's the meaning of absolute refractive index. Got the idea? Yes. Okay, so we got an idea here that refractive index of glass is around 1.5. These are all standard values. Refractive index of water is 4 by 3, which is 1.33. For air or vacuum, what's the refractive index? Actually, refractive index is speed of light in vacuum divided by speed of light in that medium. If I'm taking medium as air itself, then C by C, you'll get 1. So remember, absolute refractive index of air or vacuum is 1. Okay, so these are some standard values. Fine. Now, these values will tell you something. As I told you the meaning, that meaning only if you pick up, you can see the light goes faster in air, next highest in water, and slower in water and very slow in glass. How do you decide that? You can see the refractive index. You know what is the meaning of refractive index? How slow the light travels in that particular medium. That is refractive index. So in the water medium, light is slowing down by 1.33 times. And in glass, it's slowing down by 1.5 times. So more slow in glass than in water. So speed of, so since refractive index of glass is more than refractive index of water in comparison with air, speed of light in glass will be least, then speed of light in water, and then speed of light in air. So what does this tell you about the nature of the medium in terms of denser or rarer? Since the speed in glass is very less, don't I feel that it's more dense, thick population, densely populated? Yes. So since the speed is less, I can say that this is optically denser. Optical density is highest in glass, optical density is next in water, and optical density is least in air. Okay, that means this is more denser, this is more denser, then this is medium, and this is less denser. Okay, so this is what refractive index actually finally suggests. So finally, if you see more the refractive index, more is the optical density. So more the refractive index. So refractive index, how they are related, let us see. More the refractive index, less the speed. So inversely proportional to the speed. More the refractive index, less is the speed. More the refractive, more is the optical density. So more the refractive index, more denser. So this is how these three are related. Hope you understood this. So this is the absolute refractive index of the medium I've spoken about. There is second one which I told, relative refractive index. Relative refractive index. Now what is this relative refractive index? The word relative only tells us that it's in comparison with something. Absolute also we have compared with something, but something was that standard, right? Here, when you are comparing relative refractive index, you're comparing it with something which is not a standard one. Like if I take glass and water, say I keep a glass slab in water. I keep a glass slab in water. So light is coming from glass, light comes from water, enters glass. Okay. So what exactly happens? To understand that, you should know which is more denser, less denser, right? So when you compare these two medium, which is more denser, which is less denser, already we saw about that. But then relative refractive index also helps us here, because it's not in comparison with air, and always air will not be there. Such situations also you can come across. So when you, as I told you here, coming back to Snell's law, in Snell's law, we saw that there is some constant over here, and that constant is same for all the cases of angle of incidence, but provided medium remains the same. So if medium changes, the things are going to change. These values are going to change. That means these values depend on the nature of the medium. So what is that nature of the medium? How dense it is, how less density is, all that. So that means this constant itself is a refractive index, because that is the term which actually tells you the density, optical density of the medium. So it's very clear that this constant is nothing but the refractive index itself. But when I say refractive index, obviously when I use a standard law, I can't take absolute. Why? Because it's always in comparison with air, and that becomes a particular case. You're comparing with air. But in situations like this, you're not having glass in comparison with air. Okay, so such situations when they come, you should be ready for it. So when you give a law, it should be general. Okay, so everywhere, any pair of media, you should be able to apply it. So we have a term called relative refractive index. So that constant will be replaced by relative refractive index, not absolute refractive index. So what is this relative refractive index? It's something like refractive index of the second medium with respect to the first medium, refractive index of one medium with respect to the other medium. Okay. So already we have spoken about the refractive index, real refractive index, absolute refractive index. So we don't have to define it again in terms of speed. Since we already have learned about absolute refractive index, we can just compare the refractive index itself, absolute refractive index itself of two medium. So relative refractive index, I'll write it as n. Relative means two medium comparison. So let me write n to 1. So when I write n to 1, what do I mean by n to 1? Refractive index of second medium, refractive index of second medium with respect to first medium. Refractive index of second medium with respect to first medium. If I write n12, then what it will mean? It will mean refractive index of first medium with respect to second medium. Okay, so now n21, let me say, refractive index of second medium with respect to first medium. What is it? Relative refractive index. So it's simply the ratio of refractive index of the second medium, absolute refractive index of second medium, with comparison with the with the absolute refractive index of the first medium. So refractive index of the second medium with respect to the first medium. That means the ratio of absolute refractive index of the second medium with the absolute refractive index of the first medium. We already saw absolute refractive index formula. It is C by V. So if it is a second medium, V will be speed in the second medium. Again, this is C by V. If it's a first medium, the speed will be in the first medium. When you take this, this goes up, this comes down. So you get C divided by V2 into V1 divided by C. C and C will cancel. So you end up with N21 being equal to N2 divided by N1, which is again equal to V1 divided by V2. So this is relative refractive index. Now, after understanding this, we can complete the Snell's law. That is sin I divided by sin R is a constant. Already we discussed this, is a constant. And that constant is actually talking about the nature of the medium. And that is given by refractive index. But absolute you cannot use, I said, because it's always with air. So it is relative refractive index of the second medium with respect to the first medium. So this is a formula which you can even write it as N2 divided by N1. You can even write it as V1 divided by V2. Other form of Snell's law can be written like this. Since you can see here sin I by sin R is equal to N2 by N1. You can even write it as, you can shift this up here and this with this. You get N1 sin I is equal to N2 sin R. So this is another form of writing Snell's law. So hope you understood this Snell's law. So finally the statement, Snell's law. Statement for Snell's law. The ratio of sine of angle of incidence to the sine of angle of refraction is a constant for a given pair of media and for a given wavelength of light. Means color should be the same, like red color light means red will be have to use. That is also important factor. Yes. So that's Snell's law. So now after understanding so much about refraction, I think we can smoothly move on to how refraction happens through curved surfaces, that is lens, right? Okay, let's begin with lens. So what do you mean by lens? So lens is, you might have seen lens. In the specs, we use lens. In cameras, we have lens. Microscopes, telescopes. So in all these binoculars, we have lens. Okay, cameras. Yes. So here, everywhere we use lens. So what is this lens? When I ask what is lens, you may say glass. Okay, glass is made up of glass. Or plastic also is okay. Plastic. So what is exactly glass, plastic? It's an optical medium through which light can pass. Okay. So lens is also an optical medium. Optical medium means a medium through which light passes. Already we have spoken about it. So it's an optical medium, but the speciality of this optical medium is it has a curved surface. It is a combination of curved surface. To understand it better, I think we will first see the 4 types of lens, and then we will understand really what is curved surface and all that. So let's talk about types of lens. So we have like 4 main types of lens. The first one, we call it as convex lens. It will look like this. Convex lens. So what is speciality in this case? You can see there are 2 curved surfaces, one over here and the other one is over here. So these are the 2 curved surfaces. So this becomes convex lens. Second one is concave lens. So this type of lens, we call it as concave lens. Here also you can see there are two curved surfaces. One is over here and the one is over here. So two curved surfaces are there. Okay, then we have a lens like this. It's called plano convex lens. Plano convex lens. Then we have lens like this. This is called plano concave lens. So if you observe all these lenses, everywhere there are two surfaces. If you see this, two surfaces like this join. If you see this, two surfaces which are like this, they are combined. If you see this, one plane surface, one curved surface, they join. In this one plane surface, one curved surface, combined. So all the cases you have two surfaces. But if you see first and the second one, there are both the surfaces are curved. Third and fourth one, only one surface is curved, but that still is a lens. So lens means it's an optical medium which is bounded by two surfaces, of which at least one is a curved surface. At least one should be a curved surface. Okay, so that is lens. That's right. Lens is an optical medium bounded by two surfaces, of which at least one is a curved surface. One is a curved surface. At least one is a curved surface. Okay. So normally we will be dealing with two types of lens. One is concave and the other one is convex. So this type of lens we call it as convex, in which both the surfaces are bulged outward like this. So it's called convex. It's more thicker at the center and thinner at the ends here. Convex. Okay. And the second type of lens which we'll be usually dealing with will be this type of lens. So here it's thicker at the ends, thinner at the center. So this is concave lens. So how exactly refraction happens? Let us see in both these lenses in general first. Then let us talk about the terminologies. Okay, before, talking about image formation. We'll talk about the image formation first, and then we will go for the terminologies related to a lens. So first, let me take convex lens. How the refraction happens, let us see. So this is a convex lens. Okay. So let me say there is a ray of light which is coming from somewhere here and hitting the surface of the lens. Let me say this is air medium and this is glass medium. So obviously this is more denser. So this is a rarer medium, this is a denser medium. So if you observe here the rays entering from rarer to denser, and we have learned that time, if a ray goes from rarer to denser, if a ray goes from rarer to denser, it bends towards the normal. So this is what we have learned. So here also it's going from rarer to denser, so it should bend towards the normal. Now where is the normal for this surface? The surface is like this. At this point we want the normal. Normal is perpendicular to this. It will come like this. Actually this is a part of a circle if you see. So this normal is actually a line which comes from the center of that circle. You take a circle, this is the center of the circle, you draw a line like this, then this line will be perpendicular to this surface. If you take a line anywhere like this will be perpendicular to the surface. This you take, it will be perpendicular to the surface. But if you take a line like this, then this is not a perpendicular. This is not perpendicular. So any line which comes from the center and passes the surface, it will be perpendicular to the surface at that point. Okay. So here also the normal will be like this way. This is the normal, perpendicular to the surface. So ray should bend towards the normal. Towards the normal means it was supposed to go like this. So it will bend towards the normal means like this. Now again it changes the medium now. Again it comes from denser to outside air medium, that's rarer. So again for this surface, normal will be how? The center will be this side, no? Here somewhere. So the normal will be like this. So here normal will be this way. And when the ray goes from denser to rarer, it bends away from the normal. It bends away from the normal. So the ray was supposed to go like this. Ray was supposed to go like this, but now it will bend away from the normal, means it will go like this, away from the normal. So this is how exactly refraction happens through lens, convex. In concave, what will happen? So convex usually is called as converging type of lens. But there is one clause here, that is, if you keep convex lens in a denser medium, it will not be convergent, it will be divergent. Just check it. See here. Think you have a convex lens and say outside is denser medium. Now you have kept it in something oil or something denser, and this is rarer, let us say. The same light which comes like this, there's a normal over here. Now the ray is going from denser to rarer, it should bend away from the normal. So it should bend, the normal is like this, supposed to go like this, so bend away from the normal means it will go like this. Again, it's going from rarer to denser, it should bend towards the normal. So here, where is the normal? Normal is here like this. So normal will be somewhat like this. Like this. And the ray should bend again towards the normal. So it will bend like this way. So it looks like diverging now. Okay. So what do you understand from this is, a same convex lens, if it is kept in a denser medium, it can behave like a diverging lens. But normally its nature is converging. So let's check out now with the concave lens. Say this is a concave lens. Now one ray comes like this, falls on the concave lens. This is rarer medium. This is denser medium inside. Now the ray has to go from rarer to denser and it will bend towards the normal. For this surface, normal will be somewhat like this. Like this. So the ray was supposed to go like this, straight. It will bend towards the normal, like this. Now it's going from denser to rarer again outside. So for this surface, normal will be like this. It will go away from the normal. So like this. So finally, it looks like diverging. Correct? It's a diverging type of lens. But same lens, if you keep in denser medium, it would act like converging lens. So generally, when we draw hereafter, say for example convex, say we have a ray of light coming like this, actually it bends like this and then bends like this. When we are drawing the ray diagram hereafter, we will not be doing it like this. Instead, we will do it because we are considering thin lenses here. We are taking it directly almost towards the center and show the bending like this. So we are not showing this bending. There are actually two types bending happening, but change is very small. So we are actually avoiding that and keeping it simple this way. Even for concave, instead of showing the double bending, we just show it like this. We take it till the center and then once we bend it like this. That is just to keep it simple, and for thin lens that variation is not much. So that's why we do it that way. So hereafter I'll be doing it that way. Geometric center of the lens. One speciality of this optic center is any ray which passes through the optic center goes undeviated. Any ray you take, if it is passing through the optic center, it goes straight away like this. Any ray can. You take a ray like this, you are passing it through the optic center means it will go undeviated. You take a ray like this through the optic center, if you are passing it, then it will go undeviated, no bending. But you take a ray which is hitting somewhere else, then after striking, it will deviate its path. But at optic center, it will not bend. It will go undeviated. Okay, next. There's a line here. You can see that this line passes through the optic center and also perpendicular to the surface of the lens. Because if I say line passing through the optic center, I can take a line like this way, like this. This is also line passing through the optic center. So I have to be more precise here. So a line which passes through the optic center and also perpendicular to the surface, perpendicular to surface, also perpendicular to the surface. We call it as principal axis. We call it as principal axis. So what is principal axis? It's a line which passes through the optic center of the lens and also perpendicular to the surface of the lens. It's called principal axis. Then there is one point on both the sides of the lens at which you will be finding the incident rays which are parallel. They fall at that point, they meet at that point. So that point we call it as principal focus. We call that point as principal focus. So what is that principal focus? A ray of light which is parallel to the principal axis like this. After refraction through the lens, it's found that it passes through that point. So such point, we call it as principal focus. Any ray you take, but the ray should be parallel to the principal axis. So the ray, whichever is parallel to the principal axis, is always found to be passing through that point, and that point we call it as principal focus. Okay, that's fine in convex, but what about if it is a concave lens? What about concave lens? So if it's a concave lens, if it's a concave lens, is there a point called principal focus here? Yes, there is. This is principal axis. Let us see what happens to the parallel rays which fall on this lens. So these are the parallel rays. You know the rays get diverged. So these rays are never meeting at a point. Okay, fine. They're not meeting at the right side, but we can make them meet somewhere. We can make them meet. See here, you can make them meet here. So this point where the refracted rays appear to meet, really they're not meeting, appear to meet, or the point from where the refracted rays appear to diverge. It looks like as if the refracted rays come out from here. So this point we call it as a principal focus. So for convex, it's on the right side. For convex, you can see it's on the left side if the incident rays are coming from the left side. But if the rays are coming from right side, then the focus point will be on the left side like this. So we have two principal focus for concave as well as convex. So what is principal focus? Let's write down. Principal focus, it is a point. It is a point, okay, where on the principal axis, at which parallel incident rays meet. At which parallel incident rays meet. That is in the case of convex lens. What about concave? They appear to meet at the point. Meet after refraction. After refraction. It's a point on the principal axis at which or where the parallel incident rays meet after refraction. That's for convex lens. Or appear to meet in the case of concave lens after refraction. Or you can even write it like this. It's a point on the principal axis where the refracted rays meet in the case of convex lens or appear to meet in the case of concave lens when parallel rays are incident on it. So that's also fine. So that is principal focus. Next, the distance between the principal focus and the optic center, this distance, principal focus and the optic center, or you can take this distance also. Since we have two focus, we can have two sides also the length. So from the focus to the optic center, we call that length as focal length, denoted by small f. So what is focal length? Focal length, denoted by symbol small f, is the distance between principal focus and the optic center of the lens. So this is the focal length. And that's there for concave also. I'm not going to do that. And also keep in mind, make a note that uh, there is, if you take exact double of focal length, that means you will be somewhere over here. You can call this as 2f, means double the focal length or double the focus. That's there over this side also. This distance, what is there, you can almost treat it as the radius of curvature for this surface. If you have this surface, you have a radius of curvature coming like this to this center. What is the radius of curvature? See, this is actually a part of a sphere. So if I complete the sphere, then that sphere will have a center. That sphere will have a radius. The center, we call it as center of curvature, and the radius of that we call it as radius of curvature. So this is the part of that sphere which we are using now here. One part of the lens it is. So actually, if the lens is thin lens, only for thin lens it's applicable. If the lens is thin lens, then exactly half of this radius is the focal length, and this point will be exactly the focus, and this will be 2f. Same thing happens if you have the other part of it also. Other surface if you have, this is also part of a sphere which has its own center and the radius of curvature. So exactly half of it is the focus. Exactly the center is 2f. Okay. But this is only for thin lens. Keep that in mind. Only for thin lens, this is applicable. So almost 2f is equal to r. You have learned this actually from mirror. This is almost applicable for lens also, for thin lens only. Okay. Yes. So for today, this is enough. In the next class, I will teach you how to draw the ray diagrams for different positions of object, and how do you obtain the image. Let us see all that. So what rays we can consider to get the image, and when the objects are kept at different positions. So that we will see in the next class. Okay.